So my talk is about my experience on making the Flang runtime compilable or buildable as a runtime. So it's in the title. My first thing is about what's actually the difference between LLVM-enabled projects and LLVM-enabled runtimes. So if you use enable, everyone has probably here used that already. LLVM-enabled projects uses the compiler that CMake shows us. That could be, for instance, GCC by default in a lot of cases. And is building then usually for the host architecture, but you could also theoretically cross-compile the compiler itself. On contrast to that, LLVM-enabled runtimes is using the Clang built previously in the LLVM-enabled projects one to build the runtime itself. And that's then meant to build runtimes, which is used by compiled code that are compiled Clang itself, which is not necessarily also the same platform where Clang is compiled from, but you could have a runtime for cross-compilation from x86 to AArch64, for instance. So how does it work? If you have LLVM-enabled projects, it uses just standard CMake facilities like recurses into the projects with add subdirectory. If you use LLVM-enabled runtimes, it does something different. It registers some artificial targets, pseudo targets, and for each of these targets, it does this LLVM external project add, which internally runs CMake within a directory of your main build directory itself. So concretely, it's this directory runtimes bins usually within your own build directory. So it's an entire new build tree there. If you then compile it for normal projects, it's just CMake and Ninja handling all the dependencies. If you use LLVM-enabled runtimes, the entire system first ensures that all the dependencies are built before you build the runtime. So this includes, of course, Clang itself, but also utilities like file check, not, and so on. It also, when this builds, it actually runs the CMake command, so it does not do it during the configure step. It does it during the build step itself, and then inside the build step after configuration builds the runtime you would like. There are some options you may not know about because they are not really advertised, not even in CCMake. So you can, for instance, pass your own options to the runtimes build within your build directory. So this is done with the runtime CMake args. In this example here, you can have this from the outer projects. So if you use Clang, GCC, for instance, it would be fmax errors. If you use for the runtimes build, it uses Clang. This flag with the same effect is not fmax errors, it's ferror limit, something that always bothered me somehow. If you want to have a runtime for cross-compilation targets, you can specify it in LLVM runtime targets. And then you have different flags where you can specify what options you want to have it compiled to this. In this case, optimized for a specific processor. You also have the possibility to do a standalone build. In that case, you can actually use any other compiler, including GCC, to compile your runtimes. In that case, you specify a new different top-level directory in the source tree. It's a runtimes. Specify a runtimes build, and it chooses GCC, for instance. CMake's decisions which compiler to use, and then can build it as usual. So what's new here? So what did Flang do before? So there are also two build types. First, you use the normal in-tree build, how it was called, which just goes into a subdirectory and builds. It's this with the same compiler which Flang itself is built. But you also have a standalone build. In that case, you would use a different top-level directory. You would tell it where to find the LLVM, Clang, and MLA files, and compile it there. Special there is actually you need a second one as well, because the decimal library is used by the Flang runtime as well as the compiler itself. It's the same binary, which has a strange consequence that if you would compile it with CUDA support, CUDA Fortran, and it uses Flang uses libdecimal, which is then also compiled with CUDA support, suddenly your Flang executable has a dependency on CUDA on your system. So that's one of the less nice consequences of that one, and that one to solve. It might be already the one reason to change is already because all the other LLVM runtimes do it, and the Flang runtime would just stand out. But there are also different reasons, like for AMD specifically, we want to compile for your AMD GPU targets just as any other targets. So if you use naively, you would have for AMD GPU, you need to compile it when for your host x86, again, if your host is PowerPC, again, when it has your host is AH64, and do it's as a normal cross-compiling target saves you to do that. It's also a problem. I showed also the libdecimal, which is shared code, which comes with problems. There are different requirements for what you compile the runtime with, and you compile the compiler itself with. For instance, you can't. LTO is not supported with the runtime at the moment. It should not have anything to do with how Flang and the compiler, the runtime is compiled, but at the moment it does had to use the same flag. So what are the changes? So as you may expect it, is just use the existing system for use for LLVM enable runtimes. Just add enable runtimes flang-rt. That's one way to build it, in which case it uses, of course, Clang, just build Clang to compile the runtime. But you can also, the standalone build is still supported, in which case you do again, use the runtimes as a top-level CMake directory. But then you also need to tell it where the compiled LLVM is for all the tools and the Clang library, and you need to specify the Fortran compiler you want to use. One special is, if you probably may not have seen it yet, CMake Fortran compiler works is because we don't have a runtime yet, and CMake tries out whether the compiler is able to build and link executable, and that doesn't work without a runtime. So we just tell CMake, please ignore it, just assume the compiler works. That's done for Clang as well in the bootstrapping build, by the way. There are specific things that are a bit strange and need to continue working. For instance, there is the support for 128-bit floating point, which is dependent on whether the host actually supports it, whether you compile it. One possibility is using GCC's libquadmath. But the thing is that it's tested on the host platform where you compile your Flang on. It does not necessarily have to do anything for where you actually run your executable. That one might or might not have this libquadmath available. That kind of thing should be avoided to make the compiler dependent on the environment where it's being compiled. There are also two kinds of unit testing frameworks. So there is the G-test that all of LLVM uses, but there's some custom called non-G-test testing framework as well, which adds a bit of complexity because it's used by test for the compiler as well as test for the runtime. Windows is always its own topic, and there's experimental, this CUDA support that I already mentioned, which actually compiles the runtime using NVCC, or can be built with NVCC, which is, yeah, a bit unusual. So one of the first things we agreed on in an RFC is to rename the libraries. So on the left, you see the previous names, and we got them renamed to new names, which is more follows the convention that is used for compiler-rt. Compiler-rt libraries are called lib-clang-rt.component. You may notice there's no decimal anymore. This has been integrated into the runtime. I strongly think that if you use the runtime, you should not care about what's the internal structure on what libraries, what source code file are shared between compiler and runtime is. But for other cases, yeah, I mentioned the quad-math support, but also if you want to have CUDA, these are different, just different components in this case. And at some point, there had to be a big move of all the source files. For me, it was important to have like some clear separation, because there were cases where you had a header file, which included both things that you only could use in the runtime and only use things that are in the compiler, and I really tried to get them split apart. There were some compromises, but in total, it got off. There's some complexity where the library actually is. I'm running out of time, so I have to skip thing. Shared library is also something more consistent with the way used with the other runtimes. And there's some things left that are complex, so I still want to make the Fortran modules as well use the runtime system, or because CMake has support for Fortran, why not use it? But all other things that are too complex, even for me, that is, for instance, multi-lib support, where you basically need to know all the supported environments at the same time, and I just can't do that. So thank you.